All right, so at the end of the last video, we looked at these images and we were talking about breaking down the changes in terms of enthalpy changes that are taking place into kind of steps in a cycle. So here we've got, for example, sodium chloride. Obviously, it would be in a lattice, but here we just have it as one ionic compound. We'd have to break that solid up into its gaseous ions like so, and then we'd have to surround those gaseous ions with water molecules, okay? And remember that effectively what we're talking about here, this enthalpy change is the enthalpy of hydration. That would be the delta H of hydration. Now, I don't think I explained what the symbol was before, but it's like this, delta H, HYD, hyd. And here, this is breaking down the solid into the gaseous ions. So this would actually be the delta H lattice, although it's the opposite way that we defined it when we were studying lattice energy. Okay, when we studied lattice energy, we looked at it in terms of going from the scattered gaseous ions, like so, to the lattice itself, okay, to the kind of solid in its standard state, NaCl solid, okay. Now what's going on here in this step here, and I'll just surround that, this step here is going from the solid to the scattered gaseous ions. So effectively, it's going that way, and that's why it's really important to understand what's going on with symbols. Now, when we studied lattice energy, I said, well, lattice energy is always exothermic, it's always negative. It's correct, and the way we defined it is always going to be negative. However, if we're looking at lattice energy in this sense, okay, which I would call lattice dissociation energy, because it's talking about breaking up the lattice, then we're going to have to reverse the sign there, okay? If we're going this way, we'd have to reverse the sign because we're going from the solid state to the scattered gaseous ions, and that's going to be important when we do calculations in a moment. But effectively, if we're looking at this route, in order to find out the delta H of solution, which is, of course, let me just move this out of the way. Drag that out of the way, I can actually get rid of that. If we just jumped from here, from this solid to this here, that is basically our delta H of solution by definition. If we go back to the definition, where is it? Enthalpy change of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to give a solution of infinite dilution. So that's what we've just done here, represented by this red arrow here. Okay, now Hess's law says, well, that would be exactly the same as looking at that energy cycle in terms of, first of all, breaking up that solid into its scattered gaseous ions, and then hydrating those ions. In other words, surrounding them with the water molecules. So we've got either, we can look at in terms of the addition of the lattice enthalpy and the hydration enthalpy, which would be equal to the same as the delta H of solution, delta H of solution, sorry. And if we take away the pictures, we're effectively looking at this, okay? We've got, here's our equation for our enthalpy of solution right here. And let's say value, you need to calculate it by Hess's law, okay? So you look at other values of the different pathway that will allow you to calculate that. Well, it's quite simple, really. All you're going to need to do is look at this pathway here, going from here to here. Okay, now this is slightly different from the way they explain it in the textbook. They're using a different method. I think it's easier to understand it this way. But you do have to be aware of one important thing, okay? And I kind of spoke about this a moment ago. If we look at this as our lattice energy, we're looking at it defined in opposite terms, okay? Because by definition, we said that lattice energy was the energy in the formation of 1 mole of the ionic substance from scattered gaseous ions. But here, we're looking at lattice energy in terms of the actual breaking down of that. So this is going to be a reversed sign. That's very important. If you're using this, looking at it this way, you're going to have to reverse the sign. So So if we write an equation for how we'd calculate it, okay, we could say delta H of solution equals the delta H lattice. Remember, this can be thought of in two ways. Excuse the terrible writing, it's very hard to be writing with a mouse. Plus the delta H of hydration. Okay. Now the delta H of hydration does follow our definition. According to this equation, the delta H of lattice is the opposite enthalpy of our definition. So let's put a note in there. Okay, you're going to have to reverse the sign there. So actually doing the calculations here is incredibly simple, much more simple than the ones we were doing previously when we were calculating lattice energy. You just need to pump in the values, make sure you've got the correct sign for lattice energy here, and then it should be easy enough to get the answer. You could, depending on what data you've given, you can either calculate hydration energy here, or sorry, enthalpy of hydration energy here, or enthalpy of solution, it doesn't matter.